Welcome to my presentation video on asynchronous motors. My name is Martin Lavachka, and in this video I'm going to talk about motor application, motor control systems, motor protection functions, motor monitoring, motor starter configuration, protection coordination, and intelligent power and motor control center. The asynchronous motor is robust, reliable, and very widely used. 95% of motors installed around the world are asynchronous. The protection of these motors is consequently a matter of great importance in numerous applications such as air handlers, chillers, elevators, fans and blowers, fire pumps, centrifugal pumps, compressors, crushers, conveyors, lifts and cranes, and others. The consequence of a motor failure due to incorrect protection or inability of the control circuit to operate is asphyxiation due to the blockage of motor ventilation, electrocution due to insulation failure in the motor, and accident due to non-stopping of motor following a control circuit failure. For a driven machine, and the process is shaft couplings, axles, and driving belts, damage due to the stalled rotor, lost production, and delayed manufacturing. For the motor itself is motor windings burn out due to a stalled rotor, cost of repair, or replacement. Therefore, the safety of persons and goods, as well as reliability and availability levels, are highly dependent on the selection of protective equipment. In economic terms, the overall cost of failure must be considered. This cost is increasing with the size of the motor and with the difficulties of access and replacement. Loss of production is further important factor. Specific features of motor performance influence the power supply circuits required for satisfactory operation. A motor power supply circuits present certain constraints not normally encountered in other common distribution circuits, such as a high startup current that is mostly reactive and can therefore be the cause of important voltage drop. The number and frequency of startup operations are generally high, and the high startup current means that motor overall protective devices must have operating characteristics that avoid tripping during the starting period. In this table, there are comparisons of different kinds of motor control solutions. Four levels of protection schemes are commonly proposed that can be adapted depending on the sophistication and power of the driven machine. Conventional level, advanced level, advanced plus level, and high performance level. Conventional level or conventional protection functions apply to every type of motor application. Advanced protection functions apply to more sophisticated machines requesting special attention. Advanced plus and high performance protection functions are justified for high power motors, high demanding applications, or motors in critical processes, or whenever ground current must be measured with high accuracy. In addition, high performance protection functions are not based only on current like the Advanced Plus scheme, but also on voltage. These are the protection schemes that can be implemented to guide the operation of motors in abnormal conditions, which could result in negative events such as overheating, premature aging, destruction of electrical windings, and damage to coupling or gearbox. Here's a list of motor protection functions and the result of activation. The consequence of abnormal overheating is a reduced isolation capacity of the materials, thus leading to a significant shortening of the motor's lifetime. This is illustrated on the graph that justifies the importance of overload or overtemperature protection. Overload relays protect motor against overloads, but they must allow the temporary overload caused by starting and must not trip unless the starting time is abnormally long. Depending on the application, the motor starting time can vary from a few seconds to several tens of seconds. It is therefore necessary to feed relays appropriate to the starting time. To meet this requirement, IEC standard 60947-4-1 defines several classes of overload relays, each characterized by its tripping curve. The relay rating is to be chosen according to the nominal motor current and the calculated starting time. Trip class 10 is adapted to normal duty motors. Trip class 20 is recommended for heavy duty motors, and trip class 30 is necessary for very long motor starting. Motor monitoring. The objective of implementing measurement devices is to ensure continuous supervision of the operating conditions of motors. The collected data can be used with great benefit for improving energy efficiency, extending the lifetime of motors, or programming maintenance operations. Four levels of sophistication for monitoring scheme are commonly proposed: conventional level, advanced plus level, and high performance level that can be made accessible depending on the sophistication and power of the driven machine and the criticality of the process. Here is a list of the most useful variables to be monitored and the benefit provided by the measurement. Line currents, they are directly responsible for the conductor's heating and thus for a possible time life reduction. These are the most important variables to monitor. The current measurement also gives a direct indication of the motor load and stress applied to the driven machine. Ground current. It can be measured with the sum of the three phases if the accuracy required is not high. If high accuracy is required, then it must be measured with a ground current transformer. Average current. To know the average load of the motor, whether the motor is well adapted to the driven machine or not. Phase current imbalance. As imbalance is responsible for additional losses in the motor, phase current imbalance is an important variable to monitor. Terminal capacity level. knowledge of the remaining overload capability, and a safety margin. Motor temperature, knowledge of the real thermal operating conditions taking into account the motor load, ambient temperature, and ventilation efficiency. Frequency measures current at 47 to 63 Hz fundamental frequency. The value measured is based on the line voltage measurements. If the frequency is unstable, the value reported will be zero until the frequency stabilizes. Phase-to-phase voltage. Too high or too low phase voltages are responsible for increased motor current for a given load. Voltage monitoring is thus indicating whether the motor is operating in normal conditions or not. Phase voltage imbalance. As imbalance is responsible for additional losses in the motor, phase voltage imbalance is an important variable to monitor. Active power. Indication of the load level applied to the motor. Reactive energy. Possibility to determine the necessity of implementation of capacitors to avoid payment or penalties to the utility. Motor controllers come in different types and configurations, determined by many variables within an application. It is increasingly common for a process, machine, or equipment such as HVAC to integrate the controller and the motor. This enables the machine manufacturer to add more value and control more of the solution, therefore minimizing the risk associated with external coordination. In this diagram, you can see the various functions and their combinations forming a motor starter. A direct online starter, the simplest type of motor starter, applies to the full line voltage to the motor terminals. Jaw starting is sometimes used to store small water pumps, compressors, fans, and conveyor belts. In the case of an asynchronous motor, such as the three-phase squirrel cage motor, the motor will consume a high starting current until it has run up to full speed. This starting current is typically 6 to 7 times greater than the full load current. A motor self-starter is a device used with AC electrical motors to temporarily reduce the load and torque in the powertrain and electric current surge of the motor during startup. This reduces the mechanical stress on the motor and shaft, as well as the electrodynamic stresses on the attached power cables and electrical distribution network, extending the lifespan of the system. The motor is adjusted to the machine's load by controlling the three-phase motor's voltage supply during the startup phase. Equipment is accelerated smoothly. This lengthens service life, improves operating behavior, and smooths workflows. Electrical self-starters can use solid-state devices to control the current flow and therefore the voltage applied to the motor. Self-starters are more expensive than jaw starters, but they are widely used due to their convenience and simplicity. A variable frequency drive is a type of adjustable speed drive used in electromechanical drive systems to control AC motor speed and torque by varying motor input frequency and voltage. VFDs are used in applications ranging from small appliances to large compressors. The VFD controller is a solid-state power electronics conversion system consisting of three distinct subsystems: a rectifier bridge converter, a direct current link, and an inverter. Most drives are AC drives in that they convert AC line input to AC inverter output. A VFD is extremely versatile and often used in process applications where constant pressure or flow needs to be maintained. In addition, because the motor can be run at a slower speed and hence use less energy, the use of VFD can facilitate significant power savings. Power savings. Variable speed drivers are generally the most expensive method of motor starting, but their versatility means they are very widely used. On this slide, the different applicable standards are listed on the table. Different categories of AC contactors used for asynchronous motor control have been defined in IEC 60947-4-1. Protection coordination. Type 1 and Type 2 coordination are defined in IEC 60947-4-1. Total coordination is offered by some manufacturers. On the table, you can see the level of acceptable destruction according to the coordination types. The combination of circuit breaker, contactor, and thermal relay facilitates installation work as well as operation and maintenance by the reduction of the maintenance workload. The circuit breaker avoids the need to replace blown fuses and the necessity of maintaining a stock. Better continuity performance. The installation can be re-energized immediately following the elimination of a fault and after checking the starter. Additional complementary devices sometimes required on a motor circuit are easily accommodated. Tripping of all three phases is assured. Full load current switching possibility in the event of contactor failure. Interlocking. Diverse remote indications. Better protection for the starter in case of overcurrent and in particular for impedance short circuit corresponding to currents up to about 30 times nominal current of motor. Possibility of adding RCD for prevention of risk of fire and protection against destruction of the motor by the early detection of earth fault currents. The combination of a circuit breaker, contactor, and thermal relay for the control and protection of motor circuits is eminently appropriate when the maintenance service for an installation is reduced, which is generally the case in tertiary and small and medium-sized industrial sites. The job specification calls for complementary functions. There is an operational requirement for a load breaking facility in the event of need of maintenance. Intelligent Power and Motor Control Center is a system integrating intelligent motor protection relays in a highly dependable power and motor control center switchboard. Connectivity to the supervision and control system is provided through an industrial communications network. This solution is particularly used in large industrial sites and infrastructures with continuous or hybrid processes and whenever continuity of service is a priority. Intelligent Motor Protection Relay is the key component of an IPMCC. It is a microprocessor control device. Motor monitoring and protection are performed based on measurements from sensors such as current transformers, voltage transformers, thermal sensors, earth leakage detectors, etc. From these measurements and the settings, it determines fault conditions or potential risks for motors and operators. According to the motor protection model, an IMPR can detect many kinds of faults. It is a great improvement compared to thermal relay protection. Moreover, many complementary functions can be implemented by an IMPR like monitoring, alarming, fault recording, statistics, communications, etc. Motor Control Center is an electrical switchboard that groups all motor starters of a process to build a centralized installation. Motor starter management centralization is requested in many industries and infrastructures to facilitate operation and maintenance. Withdrawable MCC functional units, aka drawers, are used in critical applications as they are more convenient to manage in case of fault. The faulty motor starter can be replaced quickly without shutting down the whole switchboard. Fixed or disconnectable drawers can be used in less critical applications. MCC type assemblies must be fully compliant with IEC 61439-1 and 61432-2 standards to guarantee the availability, safety, and reliability of the application. In an IPMCC configuration, design verification, especially the temperature rise test, is essential because the IMPR is sensitive to heat. Furthermore, MCC should provide a dependable communication bus connection. An MCC is different from a universal cabinet in the way that the universal cabinet can only be used to accommodate a group of few motor starters. It has lower electrical characteristics requirements, and it does not provide the separation between motor starters in different functional units. Therefore, in a universal cabinet, complete shutdown will be necessary before maintenance operations or any reconfiguration of the starters. On the image, you can see an open switchboard and drawers of Schneider Electric. Compared to traditional solution, an IPMCC offers great advantage in both the project design and execution stage, as well as the operation stage. The value proposition of IPMCC for contractors during the project stage is that it improves project efficiency and reduces commissioning time. The value proposition of IPMCC for end users during the operation stage is improved continuity of service, reduced untimely downtime, reduced energy costs, reduced maintenance costs, and reduced evaluation costs and time. Lots of data is managed in an IPMCC application. An IPMCC application is typically made of 50 to 1000 motor starters. To supervise the system, it is necessary to send the motor's information such as motor status, current value, alarm, etc. The traditional wire-to-wire connection is not an efficient and cost-effective way when there is a lot of data to be transmitted. Today, communications via a network is the preferred way. We come to the end of this presentation. Thanks for watching.